Continuous state branching (CB) processes, either critical or subcritical, hitting 0 with probability 1, are investigated in this research. The unique properties of these processes and their potential applications in various fields are explored. The paper begins by discussing the well-known fact that the unique stationary measure for a CB process is the Dirac measure at 0, due to the absorbing nature of the state 0. However, this does not provide insight into the behavior of the process before it reaches extinction. In the critical case, the stationary measure is determined by the ratio limit of the n-step transition probabilities, while in the subcritical case, every stationary measure has a unique integral representation in terms of the Martin entrance boundary and a finite measure on 0, 1. A stationary measure is defined as a set of non-negative numbers satisfying a specific equation involving transition functions, and a non-trivial stationary measure of the continuous time Galton-Watson process exists and is unique, up to a constant multiple, in both critical and subcritical cases. The construction of stationary measures for CB processes is achieved using scale functions of related Lévy processes, derived from the vague limit of the potential measure. Limit theorems for the CB process conditioned on extinction in a near future and on extinction at a fixed time are proven, resulting in non-degenerate limit distributions that are of the size-biased type of the stationary measure in the critical case and of the Yaglom's distribution in the subcritical case. The conditional limit theorems for CB processes are further explored, focusing on extinction in the near future and extinction at a specific time. The distributions of ZTQ conditioned on these events are convergent as t goes to infinity, and the precise limit distributions are obtained. The limit distribution is of the size-biased type of the stationary measure in the critical case and of the Yaglom distribution in the subcritical case. The properties of the limit distribution of ZTQ conditioned on extinction at time t are also investigated, including its infinite divisibility and representation of its Lévy triplet. Continuous state branching processes are investigated, focusing on normalized transition probabilities, potential measures, and extinction times. The probability of extinction within a certain time frame and at a fixed time are discussed, along with conditional limit theorems and properties of the limit distributions. The stationary measure of a continuous state branching process is represented, assuming the branching mechanism satisfies specific conditions, with the scale function playing a crucial role. This function is a unique, strictly increasing, and positive continuous function, allowing for the definition of measures on the positive real line. The relationship between continuous state branching processes and spectrally positive Lévy processes is explored through the Lamperti transform, enabling the transformation of a Lévy process into a branching process. Fluctuation theory is employed to analyze the long-term behavior of the branching process, providing insights into its limiting behavior over time. The concept of a stationary measure is examined, focusing on the subcritical and critical cases. In the subcritical case, a unique stationary measure is proven to exist, defined as micro dx equals w x x dx, where w x is a function related to the branching mechanism. This measure is shown to be the unique stationary measure, up to a constant multiple. In the critical case, there is no stationary distribution, and instead, a subinvariant distribution called the quasi-stationary distribution, QSD, is considered. The authors characterize QSDs, stating that subcritical processes have QSDs while critical processes do not. For subcritical processes, all QSDs form a stochastically decreasing family of probabilities indexed by beta element of 0, alpha, where alpha equals psi, 0 plus. These QSDs can be expressed by the stationary measure micro. In the critical case, convergence results are established for the rescaled process QTZT conditioned on zeta greater than t, where QT right pointing arrow 0 is T right pointing arrow plus infinity. The convergence of transition probabilities and potential measures for continuous time branching CB processes is investigated. Lemma 3.1 demonstrates that the normalized transition probability PT x die on 0 plus infinity converges vaguely to a precise measure for any lambda greater than 0. Theorem 3.2 establishes weak convergence if alpha greater than 0 and vague convergence if alpha equals 0, implying that the transition probability when constrained on 0, infinity, is vaguely convergent with a rate dependent on alpha. Example 3.3 shows that for a subcritical CB process with a branching mechanism psi, the transition kernel converges weakly to a measure micro die as time t tends to infinity for every x greater than 0. This convergence is based on the monotone density theorem and the properties of the function phi. For a critical CB process, the transition kernel converges vaguely to the stationary measure micro die as x tends to infinity. Theorem 3.5 proves that the potential measure g, x, die, of the CB process has a density given by equation 3.9, involving the function w, y, related to the Laplace exponent of the associated spectrally positive Lévy process. The theorem also states that g, x, die, converges vaguely to the stationary measure micro die as x tends to infinity, established through the Lamperti transform and the monotone density theorem. The paper further explores the relationship between the potential measure g, x, die, and the potential measure u, x, die, of the Lévy process killed on exiting 0, infinity, when issued from x greater than 0. Equation 3.10 expresses the expectation of an exponential functional of the Lévy process in terms of the CB process, derived using a change of variables and the properties of the Lamperti transform. The results provide insights into the long-term behavior of CB processes and their interplay with Lévy processes. The research discusses the properties of the measure g, x, die, and its relation to the potential density u, x, die. It is shown that g, x, die, is a finite measure on 0 plus infinity if the branching mechanism psi satisfies a specific condition. This condition is equivalent to the finiteness of the integral of psi, u, do. The Lévy measure pi plays a crucial role in determining the finiteness of g, x, die. For alpha greater than 0, g, x, die, is always a finite measure. The research then moves on to the critical CB process, focusing on its properties and behavior, particularly in the context of extinction. It proves the equivalence of two integral expressions, leading to insights into the process's variance and the expectation of a specific random variable. The paper introduces a probability measure and its properties, showing it to be the size-biased stationary measure. The limit distribution of the CB process conditioned on extinction is established, involving the Yaglom distribution and its properties. Throughout, mathematical derivations and proofs support the claims, showcasing intricate relationships between mathematical concepts and their applications. The paper discusses the convergence of a specific probability measure as time approaches infinity, utilizing a lemma and the properties of the function phi, t. It then shifts focus to the distribution of zt-q conditioned on extinction at a fixed time t, involving Laplace transforms and the definition of a new probability measure. The importance of conditioning on extinction versus non-extinction is highlighted, with the use of H transforms for both cases. The distribution of z's under the conditional probability px, zeta equals t, and its relation to the martingale m, t, are also mentioned. In the context of continuous state branching processes, the paper explores the distribution of a conditioned branching process, CB process, at the extinction time. The CB process is defined as a branching process conditioned on non-extinction, and its H transform is given by equation 4.11. The main result of the paper is theorem 4.3, which provides the distribution of the CB process at the extinction time in the limit of large times. This distribution is characterized by a positive random variable VQ, whose Laplace transform is given in equation 4.13. The distribution of VQ also satisfies equation 4.14, which involves the distribution of another random variable WQ defined in theorem 4.2. An alternative approach to obtain the distribution of VQ is presented in proposition 4.4, where it is shown that z zeta chi, zeta greater than q, converges in distribution to VQ as x approaches infinity. This proposition uses the total probability formula and the probability density function of the extinction time given that z0 equals x, denoted as f eta, z0, t, x. The paper also discusses the convergence of the Laplace transform of z zeta chi, zeta greater than q, as x approaches infinity, which is equal to the Laplace transform of VQ. This convergence is established using theorem 3.5 and the dominated convergence theorem. The research paper discusses the properties of critical and subcritical branching processes, starting with the definition of the branching mechanism psi, lambda, and the scale function w, x. It provides examples of critical and subcritical processes, including their stationary measures and limiting distributions. The paper highlights the infinitely divisible nature of the limiting distributions and their representation through the Lévy triplet. The authors also explore the convergence properties of a sequence of random variables VQ and a continuous time branching process Z up pointing arrow T. Key results include proposition 4.8, which shows that VQ converges in distribution to a positive random variable V infinity under certain conditions, and proposition 4.9, which demonstrates that Z up pointing arrow T converges in distribution to Z up pointing arrow infinity sign. The proof relies on the Lévy decomposition of the Laplace exponent. The findings contribute to our understanding of the interplay between the parameters of the underlying branching process and the limiting distributions of VQ and Z up pointing arrow T. The research paper discusses continuous state branching processes with immigration, focusing on their conditional limit theorems. It establishes a general framework for these processes, leveraging vague convergence for weak convergence of finite measures. The authors prove a conditional limit theorem for critical continuous state branching processes, extending previous results. They also explore the Williams decomposition for superprocesses, crucial for understanding their structure and behavior. Applications include the study of multi-type Galton-Watson processes and their invariant measures, as well as the spectral representation for branching processes with immigration on the real half-line. The paper concludes with a detailed list of references, highlighting the breadth of literature informing its research.